In this video, we're going to be looking at measuring test effectiveness. So there's a few measures that you're going to commonly see when reading journal articles that are talking about the development of a new test to detect some kind of disease or predict something. And so there's a lot of terms that they're probably just good to be familiar with. Some that you've probably heard before in the era of COVID-19. So a couple of these we're going to kind of break down. We're going to calculate, and we're going to talk about what exactly they're measuring. So as we've talked about before, tests are typically not 100% accurate. It'd be nice if they are. Maybe there's a few that are. But most tests are going to have a little bit of error in detecting the presence of a particular disease or virus or something like that. And so to measure the effectiveness of a test, we use these different terms that measure different aspects of its reliability. So the first measure that we're going to talk about is positive predictive value. And that's going to be the percentage of positive test results that are correct. In other words, it's the probability of a correct result given the test result is positive. So one thing that I'll kind of mention about all four of these is that all four of them are conditional probabilities, which might be helpful to think about in the context of a probability tree. So as we've kind of seen before, you can chart out kind of the different situations. So like has disease, doesn't have disease, gets positive, negative, gets positive, negative. And you can kind of identify where each of these values falls because each of these are going to be measures that we would plot somewhere on that probability tree. So positive predictive value is the percentage of positive test results that are correct. So it's the percent of correct result given that the test we got is positive. So if you want to think of it this way, let's say that I'm testing for COVID-19 and my test result is positive. Positive predictive value is telling me the likelihood that I really have it, given that I have this positive test result. It's the likelihood that I really had the disease. Negative predictive value is going to be the percentage of negative test results that are correct. So the probability of correct result given I have a negative test result. Same idea, I have a negative result. Negative predictive value is telling me the likelihood that this is right, that I really don't have the disease given that I have my negative result here. Now, sensitivity and specificity are really close to these previous two things, and they're really easy to get these mixed up. But sensitivity is a percentage of truly positive people, the people who really have this thing, who will correctly test positive. So it's just flipping around the condition. It's flipping around what I'm starting with. So with sensitivity, it's the probability of a correct result given the person being tested has the condition of interest, that they have this disease or whatever it is that we're testing. So assuming if I really have COVID-19, sensitivity is the percentage, the probability that I'm going to get a positive test result. And specificity is the opposite, where it's the probability of getting a correct result given that you don't have this condition. So I don't have COVID-19. Specificity is the likelihood that I correctly test negative, given that I don't really have COVID-19. Okay, so let's calculate each of these measures from this drug test example. So this data that we've seen earlier, we have 555 adults who were tested for drugs. In this case, they were apparently honest about whether they had drugs or not because we were testing out. I honestly, again, I don't understand the context, but somehow this worked, and we know if they were really using drugs or not in relation to what the drug test indicated, if they did or not. Now, this is not a perfect test. We have some false positives, we have some false negatives, so let's calculate some of these measures of reliability. So what percentage of positive tests were correct? So what I'm going to do is I'm going to look at, this is a conditional probability. So notice this, right? So this is a conditional probability. So this is the probability of correct given we have a positive result. So let's first think, which measure is this describing? The probability that a test is correct given that the result is positive. So I'm going to go back up here, think about it for a second. this is describing positive predictive value. So starting with our positive test result, what is the likelihood that this test result is correct? That this person really has a disease given they got this positive test result. So I'm going to look here at the number of positive cases. That's going to be this column right here. And I'm looking at what percentage of them were really correct. And it looks like 45 out of 70. 45 out of 70 positive test results are for people who really were using drugs. The other 25 people were not using drugs, so they got false positives. So my positive predictive value is going to be this 45 divided by 70 equals 0.643. All right. Now the second question, what percentage of negative tests were correct? So again, this is asking for probability of correct given negative results. This is going to be the negative predictive value. So this is Ppv, this is Npv. So this is going to be this column, and it looks like 480 out of 485 negative test results. That was a terrible, I don't know what happened to my 8 there. 485 is the negative predictive value. So I get 0.989 or 0.990, depending on how you want to round. 0.990, I guess, is the correct rounding. So that means that if you get a negative test result in this case, then it's probably correct. Whereas if you get a positive test result, it's a little bit more ambiguous because 64% really do, 36% really weren't using drugs. And we're getting a positive test result here. So that means that the positive predictive value isn't so great on this test. However, that's not, like, positive predictive value is commonly a measure that is sacrificed in test effectiveness because it's kind of considered the least important. It's more important that we catch it if it's there than if we accidentally give you a false positive. So if you think about that, false positives are kind of like usually less of a concern than false negatives. All right. What percentage of drug users correctly tested positive? So this is asking for the sensitivity measure. By the way, sensitivity and specificity are words that are easy to mix up because they sound so much alike. So the way that I kind of think about it is sensitivity, like the word sensitive, means that you're more caring, you're more concerned, you're more sensitive to this person. And so I think of that in the context of truly positive people who really have COVID-19. We want to be sensitive because they have this condition, they have this disease. So associate sensitivity with people who have the condition. So the percentage of drug users, what percentage of drug users, what percentage of COVID-19 carriers correctly tested positive? So then I'm going to look here at this row now. This is going to be the people who really have the condition, the people who really use drugs, what percentage of them correctly tested positive? It's going to be 45 out of 50, which is just an easy 90%, right? 0.90. So 90% of people who really did drugs correctly tested positive. Now, finally, what percentage of non-drug users correctly tested negative? This is specificity. We want to be specific. We don't care. We're not sensitive about them because they don't need sensitivity. We're just going to be specific about what's going on. So what percentage is going to be this 480 out of 505 on that bottom row? And I get 0.95 approximately. All right. Okay. So let's look at another example. And this is an example that I would encourage you to try on your own first. Maybe you want to pause the video and then I'll go through it. But just one kind of overarching note here is that every test has weaknesses. So just because we're looking at a test and maybe one of these measures isn't so great, so like the Ppv, for example, is 64.3%. That doesn't sound so good, especially when the other measures are all like 90% and above. That's really not abnormal. when doing tests, and PPV is commonly going to be the measure that gets sacrificed, especially when we have a very low incidence condition. So I don't know if the drug one is particularly low incidence, but the lower incidence the measure is, the harder it is to get a good PPV, because you're just going to get so many false positives. Like there's just, like when you're testing, 5,000 people who really don't have the condition and only 40 who do, then there's going to be a couple of those 5,000 who get some false positives, and then you only have 40 to begin with who really are positive. So then your positive predictive value, if we start with the positive test results, how many of them really have the condition, isn't always going to be so great. And that's just the way it is when you have a low incidence condition that you're trying to detect. All right. So one thing that you can combat here, so if you want to improve that measure, what you could do is order multiple tests to be done. And that's because if I measure you 2, 3, 4, 5 times, the percent positives that are coming back should be close to the sensitivity measure if you really have the condition. It should be close to the specificity measure if you don't. So that's kind of one way, is of the people who test positive, if you just test them multiple times, then you can kind of improve your diagnosis, because then you're not prone to this maybe low PPV, but instead you can order multiple tests, and it should either converge to either the sensitivity measure or the specificity measure, depending on whether or not they really do or don't have the disease. Okay, that said, here we're screening 64,000 patients for a low incidence disease. This table shows the testing results and later confirmed results. Number 1, calculate the sensitivity and specificity for this screening test. As a reminder, this is the probability of getting a correct result given person really has the thing, really has it. I'll just write that. It's a probability for correct given they really have it. So then I'm going to look at the people who really have it. So the number of people, if you want to think about it this way, number of positive and disease divided by number with disease is really what we're doing. So of the people who really have it, they really have the disease, we're being sensitive here, what proportion of them got a positive result? And so I'm looking and I'm seeing that 132 have the disease and tested positive. And there are, oops, not that one, 177 who really have the disease. So 132 over 177 is my sensitivity measure. That's the percentage of really truly positive people that I'm catching with the positive diagnosis. So that's going to be some number, 0.746. I'll just round that. Again, ideally we use R, we'd have more accuracy, we'd care more about decimal places. This is more just kind of for approximation, conceptual understanding of what's going on by engaging in the procedures by hand, and not just depending on software for everything. Okay. Specificity. Okay, there we go. Is going to be the probability for, again, a correct result, but this time assuming that they really don't have it. And I guess, I could write, so I'm writing correct over here, the probability of correct. I guess I could also say probability of negative result, negative test, given they really don't have it, or probability of positive test, given they really have it. So either of those wordings work as long as you know what you're doing. So this is going to be the number of negative and no disease over number with no disease. And this is going to be, let's see, it looks like it's going to be this column right here. So it's going to be that 63,650 over the 64,633. So number of people negative with no disease is right here, over the total no disease is going to be right here. And the number I'm going to get here should be pretty good, I think. 0.985, I guess, 98.5%. So I have some pretty good specificity here. Like if somebody really doesn't have it, they're probably not going to get a negative test result. If somebody really does have it, though, it's not quite as great here. We're missing about 25% of the diseased people with this test. So it doesn't have a great sensitivity. So from a public health standpoint, that might not be great, because sensitivity is the more important measure if we're trying to contain an outbreak. Specificity, we can sacrifice a little bit if we're okay, with some people getting some false positives. It's not the end of the world, but certainly sensitivity is pretty important from a public health standpoint. Now, Ppv and Npv, I'm not going to talk as much about these. I'm just going to kind of do them. This is going to be, let's see. So this is correct given positive results. So correct and positive is going to be 132 over total with the positive result is 111.15. Oops, something like that. And my MPV measure is going to be that correct 63,650, correct and negative over the total negatives. It's going to be that 63,695 row total. So you can already tell my PPV is pretty bad on this. 11.8% actually. So that means that there's a lot of people getting positive test results who really don't have the disease. So I am, and again, it's really hard when you have a low incidence disease. It does happen. You're going to get a lot of false positives. This is pretty low though, I guess. And then finally, the NPV is going to be pretty good. I get 99.9%. So I'm doing pretty good. If you get a negative test result, you're probably okay. So yeah. Certainly it's better than nothing, I guess. If I was trying to predict disease incidence without knowing a test result, I would just have to know the true incidence. So this is probably a better measure than that, but still obviously with some room for improvement, I guess. Now, last question. Let's say that you are a doctor and your patient tests positive. You decide that given the low PPV of this test, you should do a large number of tests for more certain results. You complete 20 tests. If the patient really is positive, approximately how many of the 20 should be positive? So if this patient really is positive, right, they really have disease, then we're really asking the probability of correct given patient has disease. And so this is asking for sensitivity. So the percent of the 20 that should be positive should be reflecting the sensitivity of the test. So percent positive should reflect the sensitivity of the test. Now 20 might be kind of a lot. That probably doesn't sound very realistic unless they just tests are super cheap and are easy. But in general, this is what we would expect to happen. The more tests that are done, the more we should expect either the sensitivity measure to emerge or the specificity to measure to emerge to reflect whether the patient really has it or really doesn't.